liftoff of Space Shuttle Atlantis on the mission.
The next speaker is Vicky Fawcett. She's from the University of Durham. She's going to talk about monster black holes and quasars, which sounds fascinating. Remember, you can add questions via the Q&A button. So if you want to ask Vicky a question, click on the Q&A button and pose that question, and we'll go through some of those after her presentation. But Vicky, welcome.
Hi, everyone. So I'm Vicky Fawcett. I'm a PhD student at Durham University, and I'm going to talk to you today about monster black holes and quasars. So from the last talk, I saw that a couple of you had some questions about black holes. So hopefully we can discuss them in this session as well. So just a little bit about me. So I went to university where I did maths and physics, and I actually did a project on exoplanets, and these are planets that are not in our own solar system. So that was really exciting, but then I decided to do a PhD where now I look at quasars, and it's really great to be an astronomer because every day I do what I love, which is looking at space, and I get to travel to cool places. So here's a little picture of me by a couple of telescopes, which were in India. So I got to go and travel to India and use their telescopes. So, big question, what is a black hole? So hopefully everyone here has a bit of an idea of what a black hole is. They're objects with really, really strong gravity. So they're really dense, and they've got such strong gravity that not even light can escape. And how they're formed, which was mentioned before, is when really massive stars die. So they come to the end of their life, they lose energy, and then they collapse in on themselves, where then the gravity gets really strong and you form a black hole. So in order to form a black hole, you need a star that's about 25 times the mass of our sun. So a really big star, when it dies, will form a black hole. So there's two important things to know about a black hole. First off, there's what's called the event horizon. So the event horizon is basically the size of the black hole. And once you go inside the event horizon, even if you're in a rocket that's traveling at the speed of light, you won't be able to escape. So once you're within a black hole, you can never leave. The other thing is this accretion disk. So in the solar system, all the planets go around the sun because the sun has a lot of gravity. Around a black hole, we get all this kind of material and dust and objects that are going around the black hole. But because a black hole has so much gravity, they're orbiting the black hole at very fast speeds. And these speeds mean that they rub together and they create a lot of light. So when we talk about observing black holes, we can't actually see a black hole, but we can see the matter around it. So here's just a little video. So here we have a star that's about 25 times the mass of the sun, and it's coming to the end of its life. So what happens is it'll explode in a supernova where it throws off a lot of material into space. But the material that remains collapses down into a very, very dense object, which would be a black hole. And some of the leftover material from the star orbits the black hole in what we call this accretion disk. So how do we know that black holes exist? So I just said that you can't really see black holes. So, they sound really cool, but how do we even know that they're out there in space? So there's one of the ways that we can look at black holes is in these, what we call binary systems. So these kind of come in two different flavors. You either have on the left where it's what we call an X-ray binary, where you have a black hole and then a normal type star. And these are orbiting around each other. And on the right, we have what's called a black hole binary. So these are just two black holes that are orbiting each other. So first, I'll just focus on the left one to start with. So here's another little video. here we have a very massive, big, just normal star. And then here we have our black hole. But the black hole has so much gravity that it's actually stripping material away from this star, as you can see here. So all this material is falling on the black hole. It's feeding the black hole, and this creates really powerful jets, which you can see here. And these jets are really powerful in the X-rays, and these are very energetic wavelength. And we can observe these X-rays, and from this we can infer that there's a black hole system. So the other way we can observe black holes is these black hole binaries that I was talking about. And we can observe these in what we call gravitational waves. So the first detection of gravitational waves was back in 2017, and this actually won the Nobel Prize in Physics. So how does it work? Well, you have two black holes that are orbiting each other, and they're getting closer together, and as they get closer, they orbit faster and faster. So here's a little artist impression of two black holes. And eventually they get so close together that they merge. They form one big black hole, as you can see here. And this is a really, really energetic event. And what happens is it actually creates what we call ripples in space-time. So this is kind of demonstrating it, that you see these ripples in space-time, which get stronger and more powerful as the black holes get closer together. And when they merge, it creates a signal that we can actually pick up on Earth. And when we pick up this signal, we can then do all sorts of cool physics when we can work out the mass of the black holes. And we can infer that there was a black hole system that's now produced one big black hole. And this is just showing these gravitational waves passing through Earth. And it actually changes the length of objects, and we can then measure these. But don't worry about the specifics, because this is quite a complicated effect. I've added this in because I get asked this quite a lot, which is what happens when something gets too close to a black hole? So either us in a rocket or, for example, a star. Here's a nice a kind of little simulation. So here we have our star in the top left corner, and this little box is a zoom in of our star. So you're going to see what happens when the star gets closer to the black hole and what happens to the shape of the star. So as it gets closer, you can see that it's actually getting stretched out, and eventually it gets ripped apart by the black hole. And you can see some of the star gets shot off into space, but the rest of it falls into the black hole and forms this accretion disk. Okay, so size of a black hole. This is a little question for all of you out there. How small would I have to collapse the Earth in order to form a black hole? So what I mean is, if I take all the mass of the Earth and I crush it down, how small, how dense would I have to crush it in order to produce enough gravity that it turns into a black hole? So I'll just give you a second to think about it. So the answer is roughly the size of a penny or a marble. So I take all the mass of the Earth and I crush it down to the size of just a marble, and then I would form a black hole. So this just shows you how dense these objects are. And so I've just been talking about what we call stellar mass black holes, so very small black holes that are about 25 times the mass of the sun. But we can go a lot bigger than that. And this was also mentioned in the last talk, that there's something called supermassive black holes. So what a supermassive black hole is just a normal black hole, but hundreds of thousands to billions of times the mass of the sun. And we now know that in the center of all galaxies, including our own, the Milky Way, we have a supermassive black hole in the center. So I'll get back to our own galaxy, but we do have a supermassive black hole in the center, and it's called Sagittarius A star. So we think that these black holes have got this big through what we call accretion. And this just means this accretion disk of matter I've been talking about falling into the black hole. And as the black hole essentially eats more of the material, it gets bigger. So we think maybe this is how these black holes have become this enormous. So just as a little size comparison, this is a little video showing the kind of different sizes of black holes. So here's one which we call a stellar mass black hole. So this only has about 10 solar masses, and a solar mass just means the mass of the sun. So 10 solar masses is 10 times the mass of our sun. So this 10 solar mass black hole has a radius, a size of about 30 kilometers. And to put that into context, so I'm here in Durham. If I drive from Durham to the nearest city, which is Newcastle, that is about 30 kilometers. So this is really small. So we're going to go up in size a little bit. So here's another black hole that we know of. This is about 15 times the mass of the sun, so a radius of about 45 kilometers. But we can go a little bit of a step up. So here we have something what's called an intermediate mass black hole. So this has about 1,000 times the mass of the sun and a radius about 3,000 kilometers. So just for a comparison, about 3,000 kilometers is roughly equal to the size of the moon. So here's the moon for scale. These are a little bit difficult to see because they're black, but yeah, 1,000 times the mass of the sun, roughly the size of the moon. So here we have another one that's about 1,300 times the mass of the sun, and then an even bigger one, 3,000 times the mass of the sun. And now we're up to a radius of about 8,000 kilometers. But comparing these to the size of the sun, which we know is really, really big, these black holes are actually quite tiny. So what we were talking about with the supermassive black holes, here we have Sagittarius A star. So Sagittarius A star, as I just said, is the supermassive black hole at the center of the Milky Way, our own galaxy. And this has 4 billion times the mass of the sun. So you can see up here, 4 million, sorry, times the mass of the sun. And then this gives a radius of about 12 million kilometers. So you can see the size of the sun here, which we know is huge. And then the size of this supermassive black hole. So these are really monster black holes. So how do we know that there's a supermassive black hole in the center of our galaxy? Especially since we can't see black holes. So here we're going to do a little zoom in of our galaxy. So this is actual data. We're not just looking at videos and artist impressions. This is actual telescope data. So here we're seeing the Milky Way. And if you're lucky enough to live maybe in the countryside where there's not a lot of light, if you look up into the sky, it might not be this spectacular, but you will be able to see the Milky Way across the sky, and it looks a bit like this. So what we're going to do is zoom in to the center of our galaxy. So all these dots are the billions of stars in our galaxy. And as we get closer and closer into the center, you'll see that the images become a little bit more blurry, less pretty. And this is because it's actually really difficult to look into the center of our galaxy because there's just so much dust and stars in the way. So when we get to the center, what you're going to see is some observations over about 10 to 20 years, where we've observed stars right in the center of our galaxy, and we tracked how they've moved over the years. So we're almost there. Things are getting a little bit difficult to see, and I'll just pause the video here. So each of these bright dots, they're a little bit blurry, but these are individual stars. And this is right at the center of our galaxy. So what you can see is these stars are moving around this center point very fast and very what we call eccentric. Like they don't have nice circular orbits like the planets in the solar system. They're kind of getting slingshotted around the center. But we don't actually see anything in the center. There's not some big, massive star that they're all orbiting. So what this tells us, we can use physics to kind of look at these orbits and work out the mass that's in the center. We find that it's 4 million times the mass of the sun. So the only known object is a supermassive black hole. So this is another way that we have indirect evidence that black holes exist. So some of you probably have seen this in the news. We've actually got our first ever direct evidence of black holes. So this here is the first ever image of a supermassive black hole. So this supermassive black hole it's not the one in our own galaxy, it's the one in a nearby galaxy, although when I say nearby, it's still 55 million light years away. And this supermassive black hole is 6.5 billion times the mass of our sun. So what you're seeing in this image, you can see the shadow of the black hole here, and this bright kind of disk that you see, this fuzzy red disk, is actually this accretion disk that we've been talking about. So it's the really bright material that's orbiting this black hole. So how did they do this? How do you take an image, take a photo of a black hole? So what they use something called the Event Horizon Telescope, or EHT. And these are radio telescopes. So with radio telescopes, what you can do is you can link them all up together and make a bigger radio telescope. So this little world map is showing all the telescopes they used across the world. So this was a worldwide collaboration to take this image. So they used observatories in Antarctica and America, Europe, and essentially what they did is they made a telescope the size of the Earth. And this telescope was so good that if you had like a credit card on the moon and you used this telescope, you'd be able to read the numbers of this credit card. So it was a very incredibly powerful telescope, and they used this to, over 4 nights, take images of this black hole, and then they used a big supercomputer to stitch them all together to give you the image that you see. And they're not done yet. They've got 2 more supermassive black holes that they're going to image, and one of them is actually Sagittarius A star, so the one in the center of our Milky Way. So hopefully in the next year or so, you should see more of these really cool images. So we're kind of going to move away from black holes now into more of the type of objects that I look at in my research. So there's an object called an active galactic nuclei, or we just call it AGN for short. And what an AGN is a supermassive black hole at the center of a galaxy. But this disk of matter, this accretion disk, is so bright that it outshines the entire galaxy. So these are incredibly bright objects, the brightest in the universe. And we then say a galaxy is active if it contains an AGN. So we've just been talking about how the Milky Way has a supermassive black hole, but the Milky Way is not an active galaxy. And that's just because there's not enough material in the center that's feeding this black hole to make it, to make the surrounding material bright enough. So this is just a video showing a zoom in. This is an active galaxy, and you'll notice that the center is really bright. So this is what kind of we mean when we say active galaxy, is that the center is so bright that you can't really see a lot of the details. So zooming into the center of this active galaxy, this is what we refer to as an AGN. So it has this, we think it's got some dust around it, and then in the center is this supermassive black hole with a very bright disk of matter. So here you go. This is kind of zooming in. This is an artist impression of what we think the center of an active galaxy looks like. So a really bright disk of matter, very powerful black hole. So what is a quasar? So the name of this talk was Monster Black Holes and Quasars. So a quasar is the most powerful type of active galaxy, or AGN. So they're the most powerful objects in the universe, and the most powerful quasars we know are thousands of times brighter than our galaxy. So you take 1,000 Milky Way galaxies, you put them all together, and that's how bright some of these quasars are. So why are they useful? Like, why do I study them? Why do other astronomers care about quasars? So quasars are really important in astronomy and cosmology because they're so bright. So we can see them really, really far away. And in astronomy, when you see something really far away, because light takes time to travel from that object to us on Earth, we're actually seeing light from like millions of years in the past. So what cosmologists do is they use quasars to try and piece together how the universe went from the Big Bang to the universe we see today by using them to probe back in time. So this is the most, this year, the most distant quasar ever discovered was found. It has this quite boring name, J0313-1806. And this quasar is 13.6 billion light years away. And I know light year is quite a funny quantity, like astronomers use weird units all the time. So I've done a little conversion. So 13.6 billion light years away is the same as 1.3 and then 23 zeros after it, kilometers. So this is how far away it is in kilometers. And I don't even want to try and say that. But if I decided if we wanted to go to this quasar and we use the fastest spacecraft we have, which goes about 150 kilometers per second, which is really fast. If we jumped in this spacecraft and set off to this quasar, it would take 27 and then 3, 6, 9, 27 and 12 zeros after it years to get there. So this is extremely far away, and it just kind of reminds you how enormous space is. So the last thing I just want to touch upon is, how do we study quasars? So what do I do day to day as an astronomer to look at quasars? So we use these, there's these telescopes that survey the whole sky and look for quasars. And then so we can look at quasars in the optical, which is what I do. So the visible, this is what we see with, but we can look at quasars in all sorts of wavelengths. So if you know about the electromagnetic spectrum, I've already mentioned radio waves. So we can look at these quasars in the radio, but because they're very energetic, we can look at them in the X-rays as well, and everything in between. But in my work, I use two instruments that look in the visible. One of them is called the Sloan Digital Sky Survey, or SDSS, and this has 500,000 quasars. So that's a lot of quasars. But what we're working on now, and it's the new telescope, new instrument that's just come online, and it's going to be looking at the sky over the next 5 years, and it started only a couple of months ago. So this is really, hot new data. this will look at about 3 million quasars. So by the end of my my PhD and over the next 5 years, we'll have 3 million quasars to look at, and this will be really revolutionary for quasar physics. And I expect a lot of very interesting and exciting discoveries to come out of this, because there's still a lot we don't know about quasars. So I'll just end on another nice movie looking at this new instrument, which is called DESI, and it's on this telescope here. So this is in Arizona in the US, and this is just showing, they have a few telescopes, but it's on this telescope, which is called the Male telescope. And it's just a nice little movie to show it looking at the night sky. And because I do have a couple of minutes, something that I find is quite cool is the way that DESI knows where to look to find these quasars, is because there was a previous survey of the sky where they got lots of optical data, and it's actually available for anyone to look at. So this is the link here, which I can put in the chat afterwards. But just to show you how cool some of this data is, here we have the night sky, and all these dots are either galaxies or they're stars. So here's a nice galaxy here. But the thing I find really cool to just to remind you how enormous space is that if we zoom out and we keep zooming out, you can see just the amount of data that we have in the sky. So anyone can have a look at this. It's really cool. You can use it to find galaxies yourself. So here's another one. And yeah, just spend a lot of time having a look at cool objects such as galaxies and stars. And yeah, so that's all from me. Thank you very much. I've really enjoyed being here and happy to answer any questions.
Vicky, that's great. Thank you so much. Thank you so much for sharing that with us. That's absolutely fascinating. I have a question for you. Can you hear me, Vicky?
Yeah.
Great. My first question, I was watching your presentation and I saw a lovely quasar and it had, you know, JS4397, whatever it was. I want to know who names these, because I want better names for quasars. You know, I'm not saying we should call them Susie. I'm not saying they should be named after me, but I do want to understand. So, for example, you know, we name objects in the night sky. We name asteroids. I actually have one named after me. There is one named after me. I'm so excited about this. Quasars, not that I'm after my own quasar. How do we name them, and why are they such dull names?
Yeah, that's a very good question. So, you know, back in the day when astronomy was just starting, every time, you know, they found a new star, they would give it a really lovely name. But what happened was, you know, they started finding, you know, hundreds of stars and galaxies, and then thousands, and then millions, and they realized we're going to run out of cool names very quickly. So although it's boring, the way that they're now named is after the telescope that discovered it. So J is for, it's like the SDSS telescope, and then it's just the numbers afterwards is the coordinate in the sky, in a kind of funny coordinate system. So although it's boring, it makes it a lot easier to kind of name and keep track of all the quasars that we have.
Interesting. Okay, I accept that. That probably is a very sensible naming convention to have the coordinates in the telescope. That's fair enough. Okay, so I want to know a bit more about looking at really distant objects. You talked about looking at a black hole that was 55 million light years away. And, you know, I'm a space scientist. I'm not an astronomer, but I do know that light travels at 3 × 10⁸ meters a second. And so it strikes me that we're looking backwards in time at the point at which we're looking at an object 55 million light years away. So we're looking at what it looked like 55 million years ago. Is that right? Probably doesn't look like that anymore, right?
Yeah, no, exactly. So a kind of a weird thing to think about is that if you think about the stars that you see at the night sky, some of these stars might actually be dead. They might have already exploded. But because we're seeing the light from, thousands to millions of years ago, we're seeing them when they were still alive. So it's a very weird thing to think about, that we're seeing things back in time, essentially.
Yeah, it's fascinating. And the other thing that I picked up from your talk, thinking about quasars now, is you mentioned the quasar that was 3.6 billion years old. Is that right? 13.6 billion years old. And thinking about the age of the universe, gosh, that formed kind of early in the universe, right? So we're looking at an object that formed, well, tell me a bit more about that.
Yeah, so because this is about 13.6 billion years away, then the age of the universe is about 13.8 billion years ago. So we're looking at this about 0.3 billion years after the Big Bang, which still feels like quite a long time, but it's really early on in the universe, which is why astronomers love finding these really distant quasars. And there's always a lot of fuss when someone finds one like this, because we're seeing the universe really, really early on. So we can see what was the universe like back then, and how is it different to what it is like today.
Yeah, I think that's really fascinating to imagine being able to detect an object 13.6 billion light years away. I mean, that actually blew my mind when you said that. I think that's absolutely incredible. The sensitivity of the equipment and experiments we have today is just amazing.
Yeah. And it's only going to get better.
So tell us a bit more about kind of things getting better, what we're looking forward to.
So there's it's a really good time to go into astronomy. There's a lot of telescopes happening. So you've already heard the James Webb Space Telescope, which will be launched this December. So that's an infrared telescope. So everyone's getting very excited about that. There's a new radio telescope called Meerkat. So that one's got a nice name.
I love how they name these things.
A big new radio telescope that's I can't remember when that one's going to happen, but there's a lot happening in the next 10 years. So it's really great for anyone at school that wants to go into astronomy. The next 10 years of astronomy is going to be amazing, and then we're going to have loads of breakthroughs, I'm guessing. Hopefully I'll get one as well.
Of course you will, absolutely. Do you think, seeing the first image of a black hole, which came out not too long ago, I mean, that was incredibly exciting for people across the globe. Do you think that really bolstered enthusiasm for the subject more broadly when people began to see, it's quite difficult thinking about gravitational waves. Everyone got excited about that, but it's hard for people to imagine what a gravitational wave looks like. It doesn't excite the imagination. And this comes from me, and I study magnetic fields, and believe me, as they are invisible, it's difficult to get people excited about those. Show somebody a picture of a planetary surface and they get incredibly excited, because pictures really fuel the imagination. Do you think that first image of a black hole really kind of brought to the public's attention your field? And do you think it's helping gain excitement and traction, and is the field expanding as a result?
Yeah, no, I think that was it got a lot of attention, and a lot of my friends that don't really aren't that interested in astronomy, they were all messaging me like, oh, hey, have you seen this image of a black hole? It's amazing. And other people, they didn't even realize that we hadn't seen a black hole, that we were just, up to this point, I wouldn't say guessing that black holes exist. So I showed some examples of, how we previously assumed that they're there. But it was really exciting to have, an actual image to say, yes, look, these objects exist. And I think it got a lot of attention, a lot of people excited about astronomy, which is what we love. So
no, absolutely. And kind of building on that, thinking about astronomy and the public more broadly. I mean, astronomy has always, and planetary science, my area too, has always been so fortunate in that it's a very engaging subject. Who is not interested in the night sky? I mean, everyone surely has some interest, or at some point has had some interest. So we're lucky we can engage people with physics easily. But I'm interested in whether you know of any sort of citizen science programs associated with any of the work that you do or similar, things like Zooniverse, the citizen science platform, has had things like searching for particular types of galaxy, for example, in the past. Is there anything upcoming that you know of where people can get involved?
Yeah, so there's a one I think that they're trying to develop, and it's similar to Zooniverse, but it's so I work a lot with radio, and with quasars they can produce really cool radio like shapes, like they produce radio jets, and people are really interested in the different kinds of radio shapes. So there might be one coming online where you get to classify, oh, that looks like a big jet, that's just a very small radio. So that might be coming online. There's kind of things that I'm involved with. Within DESI, we do some work at schools where we let people get access to some of the cool DESI data, and they get to play around with them. So yeah, that there's a lot. There is a lot happening in astronomy, because I think it's really important that as astronomers we help get other people involved with astronomy, because that's what we want. The more astronomers there are, the more amazing discoveries we'll find.
Yeah, I couldn't agree more. And the things that you're doing, the questions that you're trying to answer in your field and my field in some sense, how did the universe form? Why does it look the way it does? Why do the objects in the universe look the way? And they're fundamental questions that people get interested and excited by. And you're absolutely right. The more of us there are studying these things, the quicker we'll move towards some of the answers. One of the reasons I asked about citizen science actually is that you mentioned at one point that the Sloan Digital Survey has 500,000 quasars. And I thought to myself, I have some PhD students. I make them look through a lot of data. I've never made someone look through 5 million images or pieces of data. I'm not kind to my students. They look through a lot of data. They don't look through 5 million. So I wondered whether, maybe one approach, if you do want to characterize some of these things, is maybe citizen science, getting other people involved to help out in the process.
Yeah.
Or maybe you are planning on looking at 5 million. Tell me more.
So it's 500,000 for the
500,000, sorry.
one, but yeah, 3 million for DESI. So it is a bit of back in the day when we didn't have that many quasars, we could just look through, say if you want to look through images of quasars, you could just do that yourself. It would take you a week. But now that we're moving to these these really powerful telescopes that are going to get us 3 million quasars, there's a lot of talk in the astronomy community of how are we going to deal with these incredibly huge data sets. And yeah, one way is to do things like Zooniverse, where we get the public to have a look through the data. So I think I'm not aware of too many upcoming projects, but I know it's definitely something that's been talked about.
People can keep their eyes open and see, if anything appears, for sure. And I guess the other way is machine learning algorithms, or teaching computers basically how to crunch the data for you and find the things that you're interested in. So perhaps you don't have to find them by eye. I'm sure that's a growing area in your field of research. Is that right?
Yeah.
And the same for us too. If you think about spacecraft orbiting the planets, we've got more data than we can look at. So we have a similar problem. I've got a question in the chat for you. Might be slightly left field. We'll see how we go.
Okay.
This person says, if we had a mirror a really long way away and a telescope, could we see the dinosaurs?
Oh, that's a really good question.
I think, yeah. So I had a little ponder about this. And I think if the telescope had already been there at the point at which the dinosaurs were alive, then maybe. But the fact is we'd have to launch it now and it would never be able to see the light from the dinosaurs. So
I'm not sure about that, but a thing that you can think about is, say that there's alien life on another planet, really far away, and they have a really powerful telescope, and then maybe they've heard that Earth has aliens on it and they want to have a look. And they look at us with their big telescope really far away, they could see the dinosaurs. They wouldn't see us because of the light the light from us is still traveling to them. So the light they have right now might be when, there's no life on Earth, or maybe it was when there's dinosaurs on Earth. So that's kind of an interesting thing to think about.
Yeah, absolutely. So I think the answer is no, we can't launch a mirror now and see the
Yes.
dinosaurs. That can't happen. But if there was somebody who was looking at us from afar, they would be looking back in time, and so they might see the dinosaurs. Yeah, very, very good question, actually. Very, very interesting. I like that thought process from that person. Thank you for that question. I'm going to wrap up shortly, but gosh, questions for you. Thinking about things falling into black holes. So if I had an object that was orbiting a black hole quite far away, so well outside the event horizon, way out, and my black hole formed, my object presumably wouldn't know that there was a black hole that had just formed. It would just be able to keep orbiting it, right? So tell us a little bit about the point at which objects start falling into black holes, because I think in people's minds, black holes are like monsters that gobble up everything around them and like suck it all in, and it's all dramatic and everything. But actually that's not the case, is it? If you're a long way away, you would just continue to orbit that black hole and you wouldn't even know that things had changed. So tell us a bit about that.
Yeah, exactly. So because people are always a little bit worried when I say that there's a supermassive black hole in the center of our galaxy. And people's first question is, are we going to fall in? What's going to happen? But because we're a black hole actually only affects really close in to the black hole. So like you said, you can just orbit the black hole forever. And it's something we call the last stable orbit. So there is a point, you can work it out with physics and I won't go into it, but there is a point that if you're beyond that point, you will spiral into the black hole. Like that's the star that I showed. But if you're beyond that point, you'll just orbit it and it's fine. It's like us orbiting the sun. You'll just orbit it forever.
Yeah, you just feel like a gravitational force from the black hole, just like you feel a gravitational force.
So they're not that scary.
Yeah, okay, good. So we need to make sure that no one goes to bed with nightmares tonight worrying about being sucked into a black hole. So I'm glad we got that one done. Okay, one last quick one for you. Things like, when something does fall into a black hole, imagine a star fell in or imagine any other object falls in, what happens? What does that process look like?
So what the actual scientific term is spaghettification.
Yes.
So when you can imagine if an object falls in, the gravity acting on say you're falling in, maybe.
Yeah, I'm falling in.
And you're going feet first. The gravitational pull on your feet will be so much stronger than the gravitational pull on your head that you will get stretched out, which is why it's called spaghettified, because you get, and you kind of saw it with the star as well. You got a nice round star, and then as it fell in, it got stretched out. So kind of that's what would happen. You get stretched out, and then if you are in that unstable orbit, you will just spiral in and fall into the black hole, and then we don't know what happens then, because we don't know what happens inside a black hole because we can't see it.
You can't get any information. Yeah. Okay. So this is a great note to end on. I'm falling into a black hole, turning into a piece of spaghetti. That is fantastic. Vicky, I can't thank you enough for joining us. That's really, really kind of you to give us your time. It's been such a pleasure listening to you. Thank you so much.